We are going to start with the topic uh, on photonics absorption, right, spectroscopy based. Photonics, right, device, of course biophotonics device, okay, devices. Okay. So, where are the useful absorption spectroscopy based devices? Okay. One, right, many of this blood analytes, okay, which are present in the body, etc., can be analyzed with this. Okay. So, blood right, can be measured, okay, in terms of concentrations. Okay. It can be oxygen level, okay, or CO2 levels, okay, etc. There can be sodium plus, potassium plus, right, chlorine. So, all these atoms, ions can be captured. There can be glucose, right, lactin, etc. They, all these analytes can be captured. Okay. So, blood analytes can be measured. Okay. Oxygen means indirectly hemoglobin as well, right, oxyhemoglobin or hemoglobin measurements, etc., it is possible. Okay. This is related to blood. This right, that is another application, that is it is also related to, which is of course as a name all of you know, pulse oximetry, right, which is right, is also very important application, pulse oximetry, which is also measurement of oxygen saturation, okay, okay, etc. There is right, one more application of this absorption spectroscopy related to right, our biophotonics devices, and that is based on molecular, right, gas absorption, trace gas absorption, okay, trace gas absorption for capturing biomarkers, okay, some of the physiological activities in the blood, in the body will and some of the metabolic activities will result in some of the trace gases, okay, generation, and they may be a marker, okay, they will act as a marker for pathological conditions, okay, maybe maybe methane, maybe ammonia, maybe ketones, some other, right, acetones, etc. They act as biomarkers for a certain pathological activities. So, trace gas absorption. So, basically towards biomarkers, which are, how to extract them, using human, right, breath. It is a breath, because they will end up with either getting exhaled from skin, or human breath, etc. Okay. So, human breath exhale, okay, human breath, right, human, right, it is possible to capture this information. So, there is one more application of this absorption spectroscopy technique, is indirectly, its indirect application is on photo acoustic, right, measurements. Okay. In some cases light gets into the tissue, goes deep inside, okay, and it will excite the molecules through absorption, and there will be some reflection, scattering, etc. We may be able to capture reflected or scattered light being transmitted back, right, to the detector, which is outside. However, since there are many scattering, right, constituents in the skin, in right body, it is very difficult that the scattered light can be easily measured and captured. Because of the scattering, the direction of propagation will change, even the because of scattering, losses will be large. So, very difficult to capture this information, but if we can induce through absorption, photons getting absorbed and produces acoustic waves in the body, then very easy to capture acoustic signals. Okay. So, it is photoacoustic measurements. So, these are this approaches. We use absorption spectroscopy as the right basic idea to capture the information about analytes, about tissue structures, maybe about trace gases, etc., as I have told you. Now, we use now we know, if we talk about electromagnetic spectrum, right. So, let us say this is maybe in terms of wavelength, or okay, wavelength will be okay. So, let us say this is wavelength, it can be converted into frequency also, it can be converted into electron volts, photon energy also, right, h nu wavelength. And so, if we see so in terms of wavelength, if we try to capture shorter the wavelength, so there is a UV region, correct. UV region, ultraviolet region is between approximately, of course, exact things may be varying, but 160 nanometer or 190 nanometer to 380 nanometer or so. Then visible region, correct, there is a visible region, okay, which is around 400 nanometer to, right, 700, right. So, in that visible region we have right blue coming into picture, okay, blue, right, region, or from indigo, the violet, indigo, blue, green coming into picture, okay, maybe green coming, sorry, yeah, green coming into picture, then right getting converted into orange, yellow. Okay. So, this green region is around 500 nanometer or so. Okay. Then orange may be 570 nanometer or so, then sorry, yellow maybe, orange may be around 590 nanometer or so, right. So, maybe around so that wavelength range is around, let us say 590 or so. Then red comes into picture. Okay. So, around 600 to 700 nanometer. So, it is red. Then near infrared range comes into picture. So, near okay, near infrared range is above 750, okay, greater than 750 nanometer, and up to maybe 1300, 400 or 500 nanometer, okay, nanometer range near, and this is near infrared range, okay, near IR, this is visible, right, this is UV, yeah, right. Then be above 1.5 to micrometer is a mid infrared range, up to 2 to maybe from 1.5 to 1000, so 1500 nanometer. So, that is 1.5 micrometer to maybe 8 or 10 micrometer. Okay. So, 10,000 nanometer, okay, 10,000 nanometer is mid infrared range, and then far infrared range up to maybe tens of micrometer far infrared range. Okay. So, this electromagnetic wave part of this spectrum interacts with various molecules, atoms, okay, etc. And this electromagnetic wave, if we consider only the electrical field of that electromagnetic wave, right, what will happen when it interacts with the atoms and molecules, the electrons in those atomic and molecular structures will start vibrating. In case of molecular structure, even the molecules, the atoms which are bounded, right, with and forming a molecule will also start vibrating, also they will start vibrating. So, because of this phenomena wherein electron starts vibrating, what will happen? Electron will start vibrating, it will produce a polarization, some displacement of those electrons based on the electrical field, right, and frequency, there will be some displacement. And if the electrons atomic structure, let us say, which consists of nucleus, electrons surrounding it, and if that electron is indirectly bounded to those nucleus, right, in terms of some spring damper you can imagine. So, if this electromagnetic wave frequency matches with the electron, this resonance frequency of this structure, the electrons will start oscillating with very large displacement, and then they will jump to the next electronic levels, energy states, and that is nothing but absorption of light. But if this interactions are not at resonance level, the electron will again occupy the same ground level, but when it is oscillating, it is producing a polarization wave, and in turn that polarization wave produces electromagnetic wave with the input frequency matching with the output, input means the output electromagnetic wave frequency will match with the incoming electromagnetic wave frequency. It will generate same output, okay, as the incoming. So, what we see is the transmission. Okay. So, through a glass window the light is getting transmitted, is in that internally in the glass window, that light is interacting with molecules, atoms, and in turn it is again, right, generated through electro means wave, this energy transfer to polarization wave. And but absorption comes into picture, then electron jumps to the upper energy level, and in absorption. So, this is just to show you that if it is molecular level, right, vibrations, etc., it can be anti-symmetric, symmetric vibrations, right, or some, right, CO2 has symmetric or anti-symmetric vibrations, etc. These are all vibrations will result in different energy levels, okay. And if the resonance frequency of that incoming electromagnetic wave matches with such resonance frequencies of this vibrations, the molecular right structure will also have various electronic transitions which will happen. Basically, you know, in case of molecular structure, the right, the distance between atoms, etc., determines the energy states. So, those energy states will start changing. Of course, there are certain rules and they follow certain rules in this energy transitions, etc., and we will observe right such bands. Although I prepared this, but today, right, but I will try to describe them with right. So, if you with right schematically over here. So, if we consider let us say this is right energy right level, and this is a displacement, right, between two atoms if you consider molecular right present. So, it will have it will have, right, a certain, right, energy level depending upon the molecular between atoms, how, what is the distance, right, it will have corresponding, right, energy levels, energy, and within this energy ground level, let us say this is a ground level, okay, this is a ground level, right, energy level. If the photon energy, incoming photon energy is so much large that it can also jump to the next, right, energy level. So, which may be, right, over here. Okay. So, there is a chance that the, right, the electron, okay, it will get displaced by some amount, but okay, it will, right, the electron from here, the ground level atom will get excited to another level. Of course, these transitions will have certain rules, etc., based on the quantum electronics, right, quantum mechanics, but based on that the electron will get transferred to the another energy state, okay, which is electronic transition. Okay. So, from one electronic transition state to another electronic transition state, it can go, and right, subsequently it will return, right, through right, spontaneous emission or stimulated emission, etc. Now, within this energy level, ground level, this is excited level, right, excited level. Right. Within the ground level energy level, there will be some vibronic, right, vibrational stages. Okay. Right. So, these are interatomic vibrational energy levels. Okay. Interatomic vibrational energy levels. These vibrational energy levels are nothing but stretching of atoms in the molecular structure, because electromagnetic wave comes, it interacts, because of the molecular structures, atomic structures, they will start oscillating, and it can be stretching, right, symmetric, asymmetric, or it can be rotation also, okay, rotations, etc. If it is stretching, right, linear, vibrational energy level comes into picture, and within that vibration energy level there are molecular rotational energy levels, okay, within this. Okay. So, okay. So, vibrational energy levels are from, let us say, this to this state, correct. Electronic energy levels are transferred from one ground level to excited level, vibrational energy level will go to the next level, right, etc. While rotational energy levels, which are, right, are this, right, they have internal, right, transition like this, okay, energy states. So, these are rotational transition, right, levels. Now, this rotational transition, as you can see that the energy, right, is very small, photon energy associated with it, and h nu, if you estimate nu from here, it may end up in gigahertz, more than gigahertz, I am sorry, it may end up in terahertz or microwave region, okay, terahertz or microwave region. So, this frequencies for this small will be of the order microwave or terahertz region, okay, frequency. But in case of vibrational energy levels, this frequencies are approximately near infrared, mid infrared, right, levels, transitions. Okay. So, this frequency, right, gap corresponds to mid infrared or, right, electromagnetic spectrum transitions, and electronic transitions are invisible region or UV region. Okay. because the energy gap is certainly large. So, they result in UV region etcetera. Okay. So, all these energy levels, okay, they have certain rules for particular vibrations, oscillations, etcetera. So, if I once again just simplified diagram. So, let us say we have energy levels where because of the vibrational and so energy levels, there are vibrational energy levels at ground level and at upper right state also, let us say here, let us say, and within this vibrational energy levels we may have rotational energy levels. Okay. Right, and this vibration band also will have corresponding right rotational energy level. This vibrational band also may have right corresponding rotational energy levels. Okay, all of them. So, these are right vibrational energy levels. Right. So, this I am repeating the previous this diagram just to reinforce. Okay. These are all rotational energy levels, right. These are all rotational energy levels, and this is electronic transition, correct. So, let us say this is ground level and this is upper level, right, electronic transition over here, right, it happens. So, electronic transition can be from here to here, right, it can also happen. So, this is electronic transition. So, these are right, it results in electronic transition. Okay. So, all these energy levels take part in terms of absorption right etcetera phenomena. Okay. So, because if microwave with a particular frequency interacts such that it matches with this rotational band gap energy, the electron may get excited to or molecular structure will get excited to the upper level. Okay. Depending upon the frequency, the excitation right energy levels will be different, but all of them will end up with some absorption phenomena coming into picture. Okay. And this absorption phenomena comes into picture, and it has a particular transition rules, okay, selection rules for vibration part. What should be the transition? Then those rules are based on the right quantum mechanics. So, if we consider vibrational transitions represented by delta nu, then this delta nu transitions will have transition can take place plus or minus 1. It can go right from right this to this, okay, transition can take place. Vibrational transition will not take place where the electron will jump to the very higher state. Okay. It can go through multiple such levels also. Let us say photon energy matches with multiple vibrational levels, then first electron will jump to one energy vibration level. From there, within the lifetime, if another photon comes, it may jump above also, right, it may jump above, it may come down also, right, with stimulated emission can also come down. So, various such strains are associated with it. Okay. And rotational energy levels within this right vibrational energy levels, they have transitions which are possible, which is either 0 or plus or minus 1, okay, transitions which are possible. okay. And electronic state vibrations are also which is represented by delta S, sorry, delta lambda, sorry, okay, I am sorry, delta, I know what is happening, delta lambda, which is plus or 0 or plus or minus 1, okay, it is represented by this. And this various transitions are applicable when excited atom comes down also, right. So, it may come down, then it can come down if it is vibrational transition to the minus 1 only, it cannot jump by 2, okay, like this, right, like this. So, all these transitions, excitations etc., depending upon the electromagnetic wave frequency will result in, right, sometimes absorption, and absorbed molecules will return to the ground level etc. So, it is right, emissions, all such, right, frequencies are possible. So, if I try to see what will happen, okay, right, okay. So, all these transitions in terms of right, ground level returning to the absorption level, or absorption returning to the ground level, or absorption will result in various such depending upon each right, this levels will allow corresponding, let us say, vibrations, right, and those vibrations in turn. So, let us say this is J1 one vibration level, J2 another vibration level, within J1 there are various rotational, right, levels. Now, from 9, right, level this, it can jump to, right, it can come to 10 also position, or from 9 it can come to. So, this is let us say plus 1, but here from 9 it can come to, sorry, this is minus 1, okay, because in terms of 9 to 9 is 0, 9 to 8 is plus 1, 9 to minus, right, 1 is P10, or it can come to R8. Okay. So, if there is an so when it comes from level 9 to here vibration transition over here from upper level to ground next level bottom level ground level, when it returns it can return with increasing, right, indirectly frequency, right, nu plus 1 it can return. So, and over here it is nu minus 1, right, transition takes place. So, there can be absorption, similarly there can be absorption in a similar way. So, short wavelength absorption short wavelength absorption is represented by R, long wavelength absorption is represented by P within those bands, okay, and no right such change in the position, okay, from 0 to again coming back to 0 here, which is represented by Q. Okay. So, these three right main bands will result in depending upon the molecular structures will result in multiple such absorption bands. One is represented by P bands because shorter wavelength right, shorter wavelengths related to P bands, longer shorter wavelengths related to R band, longer wavelengths related to P bands, and Q branch has no, right, such transitions in terms of frequency. And of course, over here it is represented by parameter centimeter inverse, okay, which is also known as Kaiser, okay, pronounced as centimeter inverse or scientist Kaiser. Okay. Right, what it means centimeter inverse? It represents even the same as the frequency. Okay. Basically, within 1 centimeter, how many number of cycles it completes, okay, is represented by that number, okay. That number is centimeter inverse, okay. So, for example, if the wavelength of light is 1 micrometer, okay, 1 micrometer, that means in 1 centimeter cavity length, 1 centimeter length, 10 raised to 4 cycles it will perform, okay, right, it will perform 10 raised to 4 right cycles, okay, altogether. So, right, number of 10 raised to 4 cycles. So, wavelength sorry, in terms of centimeter inverse, it is 10 raised to 4 per centimeter, okay, number of cycles, okay, number of cycles, is it okay. So, if the wavelength is, let us say, right, 1.5 micrometer, then around 6000 plus, right, number of cycles it will perform in 1 centimeter, right. So, that corresponds to that many, right. Well, you may think what is the use of such representation, okay, why not only wavelength or frequency, right. 1 micrometer you can even find out what is the frequency, right, C by lambda will give you the frequency, okay, right. So, if it is 1 micrometer, 3 into 10 raised to 8 divided by 1 into 10 raised to minus 6. So, which is equal to 14, right, 3 into 10 raised to 14 hertz, right, 14 hertz. So, either frequency, okay, or wavelength is good enough. Why to use, sorry, 1 minute, why to use such Kaiser as the wavelength number? Because the advantage, you will see it afterwards, most of the spectroscopy applications very easy to use such parameter centimeter inverse, because when frequency shift takes place, from one frequency to another frequency, right. So, let us say nu 1 changes to nu 2, of course, there will be some loss, right, some photons will get some energy of that photon is changed, right, altered. So, frequency, all this shift is easy to estimate based on this wave number, okay, Kaiser wave number, okay, because there is a very easy relationship in terms of, right, plus something got lost, and it is 1 upon lambda 1, 1 upon lambda 2. So, 1 upon that number, easy to add them, is not it, instead of taking reciprocal and then finding out answer, you just say frequency shift by 3000 centimeter inverse wave number. So, if the frequency corresponding to the wave number was x, 10,000 wave number was x, then new frequency is 10,000 plus 3000, 13,000 centimeter inverse. Now, 13,000 centimeter inverse you can easily find out from number of waves and corresponding frequency, you simply add it. But if I tell you frequency shifted means by some new, it has shifted in terms of wave if wavelength, if I tell you 532 nanometer and there is a frequency shift of 4000 centimeter or by some small amount frequency shifting, you will have to convert them into reciprocal, add, subtract, etc. Some mathematics becomes easier, that is all. Okay. So, wave number is another way of representing this frequencies wavelength, okay, and it is related to this. So, many of the books, spectroscopic books may represent in terms of wave number, okay, but you can also convert it into frequency or wavelength, etc. So, this all this, right, bands are basically, they represent basically absorption bands, okay, or corresponding right transition bands, okay, they represent depending upon the molecular structures, they will have different such energy bands, transition bands, etc. So, here I have shown you, if it is it is possible to excite OH radicals, CH radicals. So, using UV VIS light, and we can see the transition bands in right UV ultraviolet region, etc. Vibrational transition bands are possible with molecular structures such as H2, O2, CO2, many gas molecules. You will be able to see such transitions happening in the form of light getting absorbed per particular frequency. Why? Because there is a corresponding transition where electron gets right molecular structure gets excited, okay, and rotational transitions are also possible, okay, but the frequencies will be small, right, wavelengths will be large enough, infrared, near infrared, terahertz and microwave, okay. So, which comes to right some of the molecular transitions will be of that order, okay, energy absorption. So, we will try to make use of this ideas to capture the information about molecules, oxyhemoglobin, hemoglobin or carboxyhemoglobin or something else, right, molecular structure. So, that we will see it in the tomorrow's next class.